All right, so in this lecture I would like to come back to the time discretization of time-dependent problems. And in particular I would like to look at the prototypical parabolic equation, that is the heat equation, and what kinds of time discretization make sense and which don't. And I would like to go through, let's say, the arguments for and against some. Some of that will be pretty technical, so there's going to be a good amount of math on these slides, but I hope you can follow me. So the topic is time discretization for parabolic problems. And the prototypical parabolic equation, of course, is the heat equation that you remember was like this. So we have the first time derivative of the solution minus the second spatial derivatives of the solution equals some right-hand side. And then we have given initial conditions u at time t equals 0 equals u0. And let's say for simplicity we have directly boundary conditions. For every time t along the boundary we have to impose conditions as well. But they're not going to play a role in the following discussion. So you recall from the previous lecture that the character of these equations is diffusive. That means that if you have a sharp temperature spike at one particular location, over time it's going to blur out, it's going to diffuse. So if you put a, let's say, hot piece of metal into a cold sandbox, eventually the heat is going to dissipate everywhere. And one of the things that we would hope in cases like this is that if we know that the solution becomes more and more smooth, then over time less and less is going to happen. So one of the things we would really like to do is to have a time discretization where we can make the time step larger and larger and larger the longer our simulation goes on. And so we will be guided by this sort of principle that when the solution becomes smoother, that we want to take larger time steps, and it will turn out that only certain kinds of time stepping methods allow us to do this, whereas others don't. I should add the following. So when you look at these equations here, this is the prototypical parabolic equation. I can add lower order terms here. So I could have a, let's say, an advection term and a reaction term. Advection term would be something that involves gradient u. A reaction term would involve just u times possibly certain coefficients. As long as these terms are not too large, the system remains parabolic in character. And so everything that I'm going to say for the parabolic heat equation here is going to be true for most anything that behaves like a parabolic equation. In particular, for example, the Stokes equation, the time-dependent Stokes equation, if we wanted to. Okay, so let us look at this for simplicity using the method of lines. And I should say that I'm using this here as an example. We could do the same thing with the Rather method, but the method of lines for the analysis turns out to be a little bit more convenient in this particular case. So if I do the method of lines, the first thing is I discretize in space, and I come up with a possibly very large system of ordinary differential equations, right? So you saw in the last lecture how if I have these expansion coefficients, uj, each one of them will be a function of time, and the time derivative of this vector times the mass matrix plus the Laplace matrix times the expansion coefficients equals something on the right-hand side. There are two large classes of time discretizations. They're called explicit and implicit. And the simplest exponents of these classes are called the forward and the backward Euler method. And so let me show you how we would discretize this particular term with the explicit or forward Euler method. And we would say that this equals un minus 1 divided by delta t. That's this term here. And it is explicit or forward because the other terms here, we treat them in what we call an explicit way, namely we take the solution from the previous time step. And we also evaluate f at the previous time step. So they have their name explicit because if you looked at just an original ODE system where this matrix M would not be there, then you could solve this here for un. So you would have un equals minus a un and minus 1 plus un times delta t plus un minus 1 plus f of t n minus 1. So you could separate un onto the left-hand side, and there is you could just say un equals something on the right-hand side that can be evaluated immediately. For the ODEs that you get out of time-dependent partial differential equations, you typically have this matrix M here, this mass matrix. And one of the things people often do is a process that is called mass lumping. It's not terribly important what this means right now, but essentially what that does is it comes up with an approximation of the mass matrix that is diagonal. And then, of course, if you separate everything that contains un on the left-hand side, you have mun equals something on the right-hand side that only contains un minus 1. If m is diagonal, then solving for un is, of course, trivial, because multiplying with m to the minus 1 essentially just involves dividing the right-hand side vector by the diagonal element of m. So that's also explicit, even though we still have this matrix M there. The alternative to this is an implicit time discretization, and the simplest and most obvious version of an implicit time discretization is something that we call the backward Euler method, or the implicit Euler method. And it looks essentially the same. So we discretize the time derivative like this again, but then instead of evaluating the u here at time tn minus 1, now we evaluate it at time tn, and the same thing for the right-hand side. And so in a time-stepping method, of course, you assume that you already know the solution at the previous time step un minus 1, and you want to compute the solution at the current time step, that's un. Now I actually have mun plus aun equals something on the right-hand side that I know because I've already computed un minus 1. And this matrix A is definitely not diagonal, and I cannot make it diagonal by approximation either. The character of the Laplace matrix is that it couples neighbors, right? So there's nothing I can do about this. So an implicit time discretization always requires me to solve a linear system at every time step. So in this case, something like m divided by delta t plus a times un. And I have to invert this matrix m divided by delta t plus a. That's why we call it implicit, because it requires the solution of a linear system. So what I would like to do is I would like to analyze for these two simplest possibilities of a time discretization, namely the forward and the backward Euler method, what the implications of this are. And I should say that I'm looking at the simplest let's say, examples of implicit or explicit methods, but by and large, the consequences that I'm going to show you are true for any implicit and any explicit method as well. So let us look at this for explicit methods. So I told you that I come out with this equation, and I'm going to consider in particular the case where f is equals to 0, which makes absolutely no difference for the analysis. Everything that I show you for f equals 0 is going to be true also for non-zero right-hand sides. So this matrix A here is the matrix that comes out of the Laplace operator, and in particular it means that it's symmetric and positive definite. And one of the things that we learn in linear algebra is that if you have a matrix that is symmetric and positive definite, or SPD, then these matrices have complete sets of eigenvectors and eigenvalues. And I'm going to call these eigenvectors wk and the eigenvalues lambda k. And when I say it's a complete set, what I mean by that is that if the dimension of this matrix is, for example, n, then there are n of these wk's and n of these lambda k's, that these n vectors wk span the entire space, so I can represent every vector as a linear combination of these wk's. Then I can show that they, or I can at least make them so that they're mutually orthogonal. So wk dot wk prime is delta kk prime. And then the positive definiteness means that the eigenvalues are strictly positive. So what I'm going to do with these eigenvectors and eigenvalues is that I'm going to expand my solution variable un at the set of coefficients at time tn. I'm going to write them as a linear combination of these wk's, of these eigenvectors, times coefficients mu k at time n. Okay, and then that means that if I take this sort of expansion, so I can always do this expansion because these wk's span the entire space, right? That was the guarantee. So because I can do this, I can take this expansion and I can plug this in here. Now, let me bring everything that contains un onto the left-hand side, everything that contains un minus 1 onto the right-hand side, and then multiply through with m to the minus 1. And what I find is that un equals the identity matrix minus delta t m to the minus 1a times un minus 1. And if I take this expansion for un and for un minus 1, I find that un, namely this expansion here, equals this thing over to the right. And then what I'm going to do is I'm going to take this matrix, multiply this in here. These are just numbers. These are vectors. And then I'm going to use the wk times a is exactly lambda k. Okay, so the solution vector at time n equals these coefficients at times n minus 1 times something over here. And that's what I would like to analyze a little bit more. So in particular, I've just gotten rid of this a here, and I've replaced it by lambda k, because awk equals lambda kwk. The only thing that I still have in terms of a matrix here is this m. And so let me look at this m a little bit more. So I know that this m is a mass matrix, and that means that it's the integral of phi I times phi j. And if you think about, let's say, in d space dimensions, each one of these phi i's lives or is defined at one node, and it lives on the cells around it. These cells have diameter h, and so they have volume h to the d. And the patch of cells around each node are also of order h to the d. So the individual entries are order h to the d, and then I can show that the mass matrix is essentially something like the identity operator, because that's of course the mass matrix is a discretization of the identity operator. So I can show that the spectrum is bounded from below and above, and in particular that I can approximate the mass matrix pretty well by something like h to the d times the identity matrix. So that's going to be what I'm going to stick in here. So this is h to the d times the identity matrix to the minus 1, so that gives me h to the minus d. Okay, and of course I times wk is wk. The inverse of the identity matrix times wk is also wk. So I get this sort of equation here now for these coefficients. And the next step that I would like to do is I would like to use the mutual orthogonality of these wk's. So if I multiply from the left with wk prime on both sides of these equations, then wk prime times any of these wk's here is going to be 0, with the exception of the term in the sum where k equals k prime. And then it's 1. That was the mutual orthogonality. And the same thing happens on the right-hand side. So I get that the expansion coefficient mu k prime at time n is given by this sort of expression here, which I can compute from time n minus 1. And I can immediately see the following. So the method is definitely stable if this factor here is between minus 1 and plus 1, because then by magnitude the expansion coefficient at times tn is less than the expansion coefficient at times tn minus 1. That's what we call stable, if the expansion coefficients never grow. On the other hand, if there is only one k for which this factor here is by magnitude larger than 1, then if this expansion coefficient here is non-zero, then by magnitude the expansion coefficient at the next time step is going to be larger, and in the time step after that even larger and even larger. So you get exponential growth if only one of these factors, 1 minus delta t lambda k h to the minus d, is going to be larger than 1. And so what we need to do then is we need to analyze these lambda k's. The lambda k's are the eigenvalues of this matrix A, and they correspond to the eigenvalues of the continuous operator minus delta, minus Laplace. So I want to do this in 1D for now. And in 1D you can show that the eigenvalues of this Laplace operator are k squared pi squared on the unit interval 0, 1. K squared pi squared because I can actually write down the eigenfunctions. They are just sine k pi x. So if I take these eigenfunctions, I apply the Laplace operator to it, I get this sort of eigenvalue equation here, and you can see that outcomes as eigenvalues k squared pi squared. I can do something very similar for the discrete operator. And it turns out that for the discrete operator, I get a factor h, which comes from the integration because I multiply this test function, because I multiply the operator with a test function from the left and integrate over it. And I integrate only over the support of this test function, which has size O of h. And then so I have these eigenvalues that start at h times 1 pi squared, and they go all the way up to h times the size of this matrix times squared pi squared, because I can show that there is a limit. The highest oscillatory function that I get, that I can represent on a mesh, is not has not infinitely high frequency like for the continuous case, but I need to be able to represent this on a mesh. And so the highest function that I can represent is the one that has the form sine n pi x, where n is the size of this matrix. So the highest eigenvalue that I get is h times the size of the matrix squared pi squared. Now I have that the lowest eigenvalue is h pi squared, and the largest one is h pi squared times the size of the matrix squared. The size of the matrix in 1D is 1 over h. Okay, so I get this factor, and you immediately see from this that in 1D the condition number of the Laplace matrix, for example, is h to the minus 2. Okay, the condition number is the ratio of the maximum to the minimum eigenvalue. In d space dimensions, I can do the same thing. What I get is that I multiply with the test function, I integrate over it, so that gives me an area or a volume of the size h to the d. This k goes from something not from 1 to the dimension of a, but from something from 1 to something like 1 over h. And so the minimum and maximum eigenvalues look like this. And again, I get that the condition number is h to the minus 2 in any space dimension. So this h to the d here comes from integrating the matrix entries. This h to the minus 2 comes from the fact that we look at a second order operator. So every second order operator will yield a matrix that has condition number h to the minus 2. Anyway, the whole point of this was that I wanted to look at this particular term. So we wanted this method to be stable, and that meant that this term here needs to be less than 1. That was what we needed for our explicit time-stepping method. I know what this lambda max is now. So if I look at this, I only need to look at the maximum eigenvalue. So lambda max had this particular form, and what I find is that this delta t must be less than 2h squared over pi squared if I want this factor to be less than 1. So that gives me a limitation on the size of the time step. The method is only going to be stable if the time step is small enough. Okay? And in particular, small enough means it is less than 2 over pi squared times the mesh size squared. And this turns out to be a severe restriction, because that means in particular that if I make the mesh finer by a factor of 2, so I split every cell into 2, I actually need to make the time step smaller by a factor of 4. And that goes against everything that I wanted to do. You remember that I wanted to have a time-stepping method that can make the time step larger and larger as the solution becomes smoother and smoother over time. Now here I'm saying that not only do I have to fix the time step, I can't make it larger, but I even have to make the time step smaller by a factor of 4 if I refine the mesh by only a factor of 2. So you get the idea that maybe explicit time-stepping methods don't work so well for parabolic problems. So let me look at this whole thing again for implicit methods, namely for the implicit or for the backward Euler method. So the difference here is that I have not un minus 1, but un. I get this particular equation if I bring all the un's on the left-hand side and the un minus 1's to the right. I can do the same sort of expansion in eigenvalues and eigenvectors again. What I find is that the expansion coefficients at time n are given by the ones from time n minus 1 by this factor, 1 over 1 plus delta t lambda k h to the minus d. Okay, that's my amplification factor. So the amplification factor is this one here, 1 over the thing in parentheses. We know that the lambda k's are bigger than 0, and so if I look at this, I have 1 over 1 plus something positive that is always less than 1. Okay, so the amplification factor is always less than 1, and in other words, the implicit order method is always stable for the heat equation, for any step size. Okay, so I can make that step size as large as I want, and that does not affect the stability. Now, there's of course a price to pay. A, I have to solve a linear system in every time step, and B, maybe I don't want to make the time step too large because then the solution becomes inaccurate, but at least it remains stable. So that is something. Okay. So if you sum this up for the heat equation, what we find is that the explicit methods, I should say this holds true for any explicit and implicit method. I just showed this to you for one particular one, but it is true for any. That explicit methods are only stable if this time step is small enough. And in particular, the time step has to go to 0 as h squared. So that makes for a very small time step, very small time step if you have a small mesh size. In other words, explicit methods are prohibitively expensive. Every time step is particularly cheap because I don't have to invert a linear system, but I need to have so many time steps that it's not worth it. And on the other hand, if you have implicit methods, then they're unconditionally stable. And yes, I need to solve a linear system in every time step, but I can make the time step large. And so as a consequence of this, the generally accepted approach is that for parabolic problems, you use implicit methods. Maybe not the backward-Euler method, but let's say an implicit BDF2 or an implicit Runge-Kutta method, or any of the higher order implicit methods. But for parabolic problems, you need to use implicit methods to be efficient. So this shows what you can do for parabolic problems. And what I would like to show you in the next class then is a similar consideration for hyperbolic problems, namely for the wave equation. Because there the situation is completely different. And you will find that explicit methods are the way to go, unlike for the parabolic methods. But I'll come back to that in the next lecture then.